Okay, second video is going to start talking a little bit more about the atmosphere itself. Mainly its structure, a little bit on some speculation on how it might have originated, some means it could have happened. But the main thing will be its structure. So let's see if we can figure that out a little bit. One of the interesting things about the atmosphere is what occurs one area of the world can impact another area of the world. In other words, we're not separate little entities. In other words, what's happening in the United States may have been very well triggered by something that's happened somewhere else. And believe it or not, this is just a picture of a dust storm coming off the Saharas and moving across in the tropics. We're going to talk more about that later, but you can actually see these in the summertime and during the year where they'll move across. They're triggered by thunderstorms in the Sahara Desert, push up dust, cause it to come all the way across and sometimes into the southern United States, and it actually gets quite dusty. You can actually see visibilities get lower and not being able to see very well with the dust. So here's an example of one area of the world impacting another. And dust can impact things like algae blooms and all. Weather can go very quickly from very nice to very bad. So looking at the Earth as a whole, we look at the Earth as a system. What does that mean? Well, everything that works together to make the Earth what it is. There's an atmosphere, which we're going to spend a lot of time in. There's a hydrosphere, the water areas, a geosphere, geology, volcanoes, and the biosphere is plants, biology. Think about it. The atmosphere is really relatively thin. Half of the mass of the atmosphere is found within 18,000 feet of the Earth. 99% of the mass of the atmosphere is found within 20 miles of the Earth. Think about it. If you ran a marathon, you'd be at the top of the atmosphere if you did it in vertical. So the lower part of the atmosphere is made up, and these concentrations hold all the way through. In other words, if you climbed the mountain or went to the highest mountain, Everest, you would still find that 78% of the atmosphere at that height was made up of nitrogen, 20%, almost 21% is oxygen, argon, and then all the way down to 0.04% carbon dioxide. So they're there all the way through that layer. One difference is you would think, oh, you can breathe well. Well, there's less and less atmosphere the higher up you get. So that 78% of nitrogen is 78% of a lot less air. So oxygen is O2. There's also aerosols that come into the atmosphere. Think about it. Dust would be one. Ocean spray coming up out off the ocean. Forest fires. Maybe a volcano erupted. Back in the 1930s, there was the Dust Bowl out in the Midwest that was caused by some agricultural practices we were using at the time. We've gotten a lot smarter. But what it did was triggered a lot of dust storms. And that dust was in the atmosphere for days. Water vapor is a part of the atmosphere. It actually makes up upwards of 4% of the atmosphere in the lowest 1 kilometer. Oh yeah, it doesn't go too much. It's much less above that. But we need that for clouds and precipitation. CO2 varies due to photosynthesis. So in the summertime, plants are really absorbing CO2. In the wintertime, not so much. So the CO2 actually rises the amount of it in the air in the winter compared to the summer. Pollution. Some of it's man-made, some of it's not. As I just showed, we showed at the beginning here, Sahara air coming across with all that dust. That's probably not man-made. However, you can see here a picture of the smog that has occurred in Los Angeles. You get the haze and all. When they had the heat wave out in the Northwest a few weeks ago, it generated a smog layer across Seattle and some of the mountains there. So all that is natural occurring, or some of it's unnatural occurring. The scientific method. Well, let's think about this one. I'm going to describe it in terms of something that I worked on in meteorology. If you are interested in understanding why some thunderstorms could move from Ohio and West Virginia and across the Appalachians into eastern Virginia, and other ones did not. And that was a very good question because we didn't understand fully why that happened. We could summarize it. So we made some hypotheses. One was about stability. Some other were maybe wind direction. And what we did was then we went back and checked and said, okay, we analyzed this. We tested those results. Did they make sense? And what we did find was that if you combine stability and wind direction together, and you had the two factors together, we actually could understand, oh, this day, these thunderstorms are probably going to die. And they did. And other days, this factor was such that we knew they were going to continue. And yes, they would continue all the way to the ocean. So this is how you go about the scientific method. You have a question you're asking, you want to figure it out, you come up with some hypotheses, you analyze those, you look at your results, maybe go back and redo the whole thing again because it just didn't work. In our case, we had to look at two different variables to make it work instead of just one, and we looked at one each individually first. They also study the atmosphere with models, such as Purdue's tornado vortex chamber, where you can actually look at a simulated tornado. Numerical models. Observing. One of the biggest things is understanding what the weather is right now. The more observations, the better you'll know that. So ASOS is one tool that we use to do that with. ASOS is all major airports have ASOS. Why do they have them? Because they want to be able to determine if they can fly or not. An aircraft can't land under certain conditions or take off under certain conditions. So by having weather observations there, they know what those conditions are, and they can make that determination. Some other networks that are out there are cooperative observer networks. These are put out by the National Weather Service around the whole country. The idea is to get a climate database. They've been doing it for years, and we're slowly developing one. And basically each day, a volunteer will go out, check the temperatures, check the precipitation, and report it back at the end of the day to the National Weather Service, who will then track it, and we'll come up with the 30 days statistics for that location. And there are thousands of these across the United States. Sometimes we can get a little more real time than at one time a day, because it's kind of nice to know, well, how much precipitation did they get maybe in a thunderstorm, which may not occur may occur much earlier in the day than when we would normally receive the reports. Another area, COCORAS, which is all volunteers, people reporting rain, hail, and snow. Radiosondes are just a way of looking up in the atmosphere. It's just a balloon that carries a set of instruments aloft, and they generally burst because the balloons, remember, as you're going up, there's less and less air, so the balloons are just kind of spread out to get wider and wider until they finally say, oh, I can't do it anymore, and they're going to pop. And then the instruments come back down on a parachute. But they're taking readings all the way up every few seconds so that we get a profile of the atmosphere, called a sounding. And there's a radiosonde. Dropsondes are like radiosondes. They have the same kind of instrument, except they're dropped from an aircraft. So instead of going up to get a profile, they're going down. These are particularly used in hurricanes, over the water, things like that, to try to get an idea of what the conditions are below that aircraft. Remote sensing is just looking at satellites and radar. Here's a profile of the atmosphere. Notice temperatures always are dropping in the troposphere. Almost all the way there's a steady drop of temperature in the troposphere. It's going to warm back up in the stratosphere. It's going to begin to cool off again in the mesosphere, and then gradually warm way back up in the thermosphere. All these are done based on different chemical reactions that dictate temperature changes in loft. In the troposphere, we're looking basically at the air getting thinner. As the air gets thinner, the temperatures get colder. Auroras are just found from the ionosphere, and they're caused by the solar wind. You can see here, the stronger the solar wind, the more and more area covered by a potential aurora. So basically, we just talked about all the different gases that are in the atmosphere, the broad structure of the atmosphere, and all. So let's just look a little bit at a couple things to go along with this. This is just a radar. This is a radar that's literally in Ohio, and you can see here reflectivity showing the rainfall rates. The more oranges and red, the more intense the rainfall. It looks like there's been a lot of rainfall in this area with Ohio. If I were to switch this and look at velocity data, you can actually tell wind direction and how the particles are moving with time. Another one to look at is satellite. This is just a visible satellite picture, basically. The highest resolution I can get. Shows puffy clouds here. And notice how the clouds are very bright. They reflect a lot of the light back from the sun. It's in the sky where the satellite is. Notice how the green down towards the ground doesn't reflect as much. So big forests and all won't give you as much reflection. Water doesn't do it either very well, does it? A little bit darker out over the water areas. But these are all streets of clouds that you're looking at here, and you can just see them. Really some very impressive thunderstorms up and off of Michigan, moving through there. Some more in Ohio in this band that's been going through. And when we looked at the radar back here, if it comes up with those velocity data as well, that would be the same area that we were looking at here. And the final thing, if I wanted to look at the models, this is just a simulation of where the rain's going to be today by a numerical model. It goes out 18 hours into the future, and it's run every hour. There are numerous different types of numerical models out there. It just gives you an idea of what these are. So, again, if you have any questions this week, please don't hesitate to ask.